Hello everyone, I'll be going over my presentation on minimizing pose recognition architectures. So on the agenda today, we have an introduction into what pose recognition is, what are some of the data sets that are available for this problem set, an explanation of the PostNet architecture, where that's the architecture that's the primary foundation of the work that I'll be doing here, and then how we're throwing caution to the wind, and some k-means magic to kind of tie everything together, and then some of the final takeaways of what the actual implementation and the results of this method look like. So in general, pose recognition is a study of estimating the pose that a human is in by using just images. So you can see on the right here, we got Albert Einstein. He's walking along. You can see we're kind of able to reconstruct the general shape that his body is in just based on that image. So modern research into this includes a number of different fields like transformer architectures, classifiers, many different things, including just traditional convolutional neural networks, which is what we'll be looking into right now. So in terms of data sets that are available for when you actually go and attempt this, the two most common that you see are MPII and COCO. There are more that are out there, like H3.6, but in terms of accessibility and like documentation and available tools, MPII and COCO are by far the most widely supported. So those are the two that I chose to interface with as well. The exact way in which I had to interface with them was a little bit complicated. So essentially, I merged both MPII and COCO and did some key point processing for COCO because it has, for one, the nose is a key point that's in MPII, but not COCO. So you got to kind of do some processing on the back end to make everything work together and move some key points around. But essentially, by creating a unified data set between MPII and COCO, I can treat them both identically and make the training pipeline more cohesive. So from there, we go through the no object filter, which is essentially just for COCO actually, because common objects in context includes things that aren't human. So we essentially have to filter out all the images that don't have humans in them because we want to do pose recognition. And then we do bounding box cropping / filtering. That's essentially looking at where the human is in the actual image and trying to crop the area so that we're training on a more effective basis. Because there might be certain images that have the human like a mile away, where it's like, okay, yeah, they're in the frame, but you're not really getting any useful information out of that training sample. So that's what that means. And then from there, we generate some heat maps, which we'll go into what heat maps are later. And then we just split it. Our train validation and testing split was 80, 18, and 2. That's because we just had so much to work with. We didn't actually need that much stuff we didn't need that significant of a percentage in the testing set. So we decided to keep it kind of low. In terms of how models work, we'll touch on so I mentioned the heat maps here. So essentially, the heat map is a representation of how likely a certain area is to be what it's attempting to classify. So you can see on the top we have nose, shoulder, wrist, different features of the skeleton. And we're essentially trying to put a blob over where that is in the image. And you can see this is an example of what a good output to that would look like, where you're seeing the blob is centered right over the feature that you're trying to classify. And so what you're looking at with most of these architectures is that they essentially take the image and process it down into these heat maps, where you can then take some additional processing to be able to figure out where those actual features are. You might use some statistical processing. You might just do something really simple like find the maximum value and just use that. But essentially the modern cutting edge is just focused on, at least part of the cutting edge is focused on honing these models and making them more accurate to where the actual features are. So in terms of the one that we'll be using PostNet. That's a heat map architecture, but it essentially is a very flexible architecture, is why it finds its way mostly onto, actually I say mostly, but it finds its way onto low power devices as well as high power devices just because it's so flexible and generalizable. But that flexibility also lends itself to people like me who want to take it apart and figure out how it works. So in terms of how we're actually going to simplify this, I decided to just see how much I could reduce the output space by and still get a reasonable result on the other end. So the first thing I did is, if you recall, there were a bunch of like points around the eyes for PostNet. We don't really need that. I just decided to have one point on the nose for the head position and then track everything else. So that's 4 out of the 17 points completely gone. So that's essentially almost a quarter reduction in the size of the output space just by removing some points that we don't really need. From there, we're going to try something a little scary. Essentially, if you think about what the actual heat maps are doing, they're identifying right shoulder, right elbow, left elbow. But I decided to see what happens if you just do elbow and try and split them later on. So essentially, rather than having one heat map just for the left elbow and one heat map just for right elbow, you just have a singular heat map for the elbows, which you then split later on. So this essentially cuts your output size in half. And it could theoretically also make your model simpler, since it doesn't have to differentiate between left and right elbows anymore. It just has to find elbows. So we'll look at exactly how let's look at exactly how we're going to split that heat map. So this is where the k-means comes in. Essentially, if we apply a threshold to that heat map, we get some clusterings of points, which we can then, since we know everybody has 2 elbows, we just apply k-means clustering with 2 clusters, and then we can use the centroids as the actual location of each feature. So in terms of our full architecture, now we've got it kind of assembled. So that blaze pose bounding box, you don't have to worry about that. That's a different part of the architecture that comes from essentially cropping down the image. But we then go into our reduced PoseNet model, which is the PoseNet architecture, but just with a bunch of layers removed. And then I didn't relabel that, but essentially that's supposed to just go straight to k-means. But then our k-means gives us the actual end-up skeleton. I do feel like I need to mention here that I was never able to get the reduced PoseNet model to work, even though it theoretically should have. So there were a number of attempts to train this model, but partially because I'm a noob at this stuff and I suck at convolutional neural networks, I couldn't get this to work in time. So take the end results with a small grain of salt. But given my research, there's no reason why this architecture shouldn't be able to work. Just someone smarter than me has to train it. So essentially, in place of that the smaller PoseNet model, I put in a restricted PoseNet. So essentially, it's the full PoseNet architecture, but I do some additions, and I essentially take the left elbow and right elbow heat maps and add them together to kind of simulate what the smaller PoseNet architecture would look like. So it's not perfect, but we're demonstrating the technique at this point. So how does the k-means stack up? This is something I was particularly concerned about because k-means is particularly hard to do. So on average, the convolutional neural network took 880 milliseconds, whereas the k-means took 249. So it's definitely faster than the convolutional neural network. It's not negligible, but it's not 5 times longer than it takes for the convolutional neural network to run. So it's not too much of an ask to factor this into an architecture. In terms of results, we can see it's actually performing pretty well. You can see me kind of doing some random poses around the room, just kind of testing things out. Now there are some limitations. Firstly, you can filter out for multiple people and do some processing. I haven't had time to implement that, so when you put in multiple people, it freaks out. Additionally, if you have, it doesn't filter out if objects aren't in actual frame. So you can see me on the right, I don't have my legs in frame, and the model has no idea what to do with it. So that's some of the limiting factors, so you can kind of take that into this graph here, where we're graphing the mean squared error between my model and a different model called MediaPipe, which is one of the publicly available models that's kind of referred to as it's one of the better models out there, I guess we could say, where we can see that my model is performing much worse than the status quo, but it's still within the same ballpark. But I'm willing to chalk that up to the problems with multiple people because the data set was composed of single person, multiple people, bottom-up images, things that the model just really sucks at. So what does it look like in practice? You can see it's taking around a second per frame, but it's still able to do this in roughly real time. And with additional optimizations, as well as probably reducing the model size, as we mentioned previously, it could definitely get much faster and much smaller than it currently is.